Hello everyone. In this video we're going to be discussing the tree implementation of Union Find, which would be eerily similar to the linked list implementation. Really the only difference here is that instead of using a linked list we use a tree, but almost everything is identical. So in front of us we have various trees that represent our disjoint sets. The first one there has x1, 5, 6, 11, 12, and 13. The next one has 2, 7, 14, and 15, and so on. There's a bunch of different disjoint sets. The way we will implement most of the methods will be nearly identical to the way we did before. Our representatives for these different sets will be the roots of the tree, where with the linked list version we used the head of the linked list. Seems like a reasonable way to implement it. And to union these together, you might have several ways you think about doing it. One of the most obvious ways, let's say we wanted to do union x12 and x7. So x12 lies in the first tree and x7 lies in the second tree. One way you might think to do that would be to take x2 here and attach it to x12. But this has an unfortunate consequence of radically increasing the height of the tree potentially. So that's not actually a good way of doing things. Instead, let's attach x2 to the root of the tree containing x12. That seems like as good of application as any. So, just like we did with the linked list implementation, all we're really doing here is going to be rearranging pointers when we do our union. But we may also need to find the root of the tree, like we had to find the head of the linked list. So, let's see how this gets implemented. If we scroll down, make set, we simply set x to be its own parent. To find the set, we find the root of the tree, which is the node whose parent is itself. So that's pretty straightforward. And for union, what we're going to do is find the root of the tree for x and the root of the tree for y, and then attach the root of y to the root of x, just like we saw above. These run in, just like we saw before. This one is in O of h, where h is the height of the tree. This is theta 1, and this is in O of h. So, we have a decent upper bound, but like we saw before, we might be able to make this better or worse. A problem with this implementation as we have it here is that the height of the tree we know nothing about. We want our trees to, in a generic sense, be somewhat balanced. So, how could we do that? Well, one way to do that is to always attach the shorter tree to the larger tree. So, if we scroll up here, let's say we wanted to do an operation of union x16 and x6. x16 lies in the tree on the far right, and x6 lies in the tree on the far left. We could implement this in one of two ways. We could either attach the tree with x16 to the tree with x6, or the other way around. Which one of those would be more efficient? Well, the tree containing x16 has a height of 3, and the tree containing x6 has a height of 2. Therefore, we attach the tree containing x6 to the tree containing x4. And then if you notice, that doesn't even adjust the height of that tree. The resulting height is the same. And that will tend to happen. In fact, we could improve this, O of h, to be an O of log of n, and O of log of n. by making our implementation more intelligent. Determine which of the trees has a smaller height, and then attach the smaller tree to the bigger tree. And as I did with the linked list, we are not going to go through the implementation. If you want, that is included in the notes, and you can prove the correctness of that theorem inductively. That is not super important to us. It's important that you can apply these operations. So as long as you understand how we perform the union operation, as it's written here, and could perform the union operation where you always attach the shorter tree to the larger tree, you are entirely capable of solving problems that we would need to solve with this data structure. And that is really all we have for union find. This can be used for various applications. In particular, it's useful in graphics, but we aren't going to dig deep into the applications. In this course, we're more interested in talking about this is a data structure that exists and can solve various problems that you might have. This one solves the problem of needing to represent disjoint sets. And that is it for union find.